Hello again, this is the video pre-lesson, if you will, for the biostatistics lecture, PHA 3030. Topic for today is normal distribution, t-distribution, and confidence intervals. First we're going to talk about the normal distribution, then we'll talk about distribution of sample means and what's called the standard error of the mean. That'll probably be in a second video. Then we'll talk about the distribution of sample means when the sample size is smaller, less than 120, and why that's important. And we'll finish with a discussion of how to calculate confidence intervals and what they mean, although that will run throughout the second two videos. But the first video will just be about the normal distribution, the so-called Gaussian curve, and standard deviation and z-scores. This is a classic normal curve just drawn. It's a population of values. It's a mathematical construct. It's not actually anybody's real data. It's perfect. All the data fall on the line, if you will. It has a lot of characteristics. It is symmetrical. It's unimodal. It has just one mode. It's also the case the mean is equal to the median is equal to the mode. It's asymptotic, which means really it never gets to the very bottom. You can see here that it gets towards zero. Theoretically, that gets to smaller and smaller, but never really gets to absolutely to zero. That's true on this end and this end. Just a fine point, I guess. It's continuous. It's a smooth curve. Theoretical. If this is a population, normal curve is sort of a theoretical, so it's from a population, then you'd use a Greek letter on that. And the standard deviation would use the Greek letter sigma. The most important points, though, are that it's symmetrical, it's unimodal, mean equals median equals mode, and it has an inflection point, we'll talk about that in a second, and a very specific distribution of data. So this is a hypothetical only. You never have actually a fully normal distribution of data. You try to approximate that. So what are two of the other characteristics? We mentioned this before. There's what's called an inflection point. That's where the curve changed from going this way on the slope to going that way on the slope. That's at this point, and on this side of the curve it's the other point, going from the slope going down to the slope changing in that direction. This inflection point is essentially exactly one standard deviation from the mean in this direction and that direction for every normal curve. This defines a normal curve. If it's a normal curve, the mean is equal to the median is equal to the mode, unimodal, and if you move one standard deviation away from the mean, above the mean, you end up with this change in slope right here. If you move one standard deviation below, you get this change in slope here. What also happens is that with the normal curve, a very precise amount of the values will show up between the mean and one standard deviation away. For every normal curve, no matter what the actual values are, when you go from the mean to one standard deviation above the mean, you capture 34.13% of the values. That's by definition. Similarly, if you go below the mean by one standard deviation, you capture 34.13% of the values again. So you could also look at it and you could say between one standard deviation below and one standard deviation above the mean, you capture 68.26% of the values. That's simply by definition. For the normal curve, it's also the case if you move two standard deviations below the mean, you get the 34.13, and you get another 13.59% of the data. And so you get, what does that add up to? 47.72% of the values. I think that's right. 13 plus 34 is 47. 59 plus 13. 47.72% of the values between the mean, two standard deviations below. On the other side of the coin, 72% of the values between the mean and two standard deviations above the mean. So if you go in all the distance between two standard deviations below and two standard deviations above in any normal curve, you're going to capture about 95.5% of the data. And that's just a given for a normal curve. So what are z-scores? Z-scores are standardized scores that are derived from a normal curve, and they're measured in units of standard deviations from the mean. In a classic z-scale, the mean is given a value of 0. If a score is 1 standard deviation above the mean, it's given a value of 1, plus 1. If it's 1 standard deviation below, it's given a value of minus 1. If it's 2 standard deviations below, it's given a score of minus 2. So you can essentially normalize scores using a z-scale. So this is a standardized z units. Again, this is a normal curve, the inflection point. The mean is given a score of 0 on a z-scale. One standard deviation unit above, where you go from the mean to 1 above, you get 34.13% of the data. That would be a z-score of plus 1. 1 standard deviation below would be a z-score of 50 minus 34.13, or basically 15.87 would be the percentage. Because it's 50th percentile here, you're losing 34.13% more, so it's 84.13 below the mean, so it's 15.87 percentile right there. If you move 2 z-scores above, if your z-score is 2, you're 2 standard deviation units above, and so on and so forth. This is an important point. If you're 2 standard deviations above if you're between a z-score of plus 2 over here and minus 2 over here, you captured about 95.5% of the data because it's 2 standard deviations on either side. And that's defined as the normal curve. But a lot of statistics isn't based on 95.5%, it's based on 95%. You've heard of the p is less than 0.05. And essentially, if the z-score is 1.96, which is just inside this 2 plus 2 and just inside this minus 2, so from right about there to there, that period from here all the way to there captures about 95% of the data. In every normal curve, 95% of the data are located between a z-score of minus 1.96, just about there, and plus 1.96, just about there. So that's the normal distribution. We're going to take a break at this point. You might want to watch this again if you're so excited about it. We'll pick up with the distribution of sample means and the foundational material for standard error of the mean in the next video.